Minecraft is a block game, and famously, it is difficult to build accurate circles, and most people just use online tools to help them. But I feel like it would be much cooler if you didn't even have to exit Minecraft. I present to you the Redstone Digital Compass 1000, a redstone circle drawer. Let's first set the scope. I want to build a redstone machine that can draw the smoothest circle possible, given any radius of length 1 until 15 that the user types in with just the press of a button, and in a somewhat reasonable amount of time. But in order to get here, we must first jump through several hoops, such as us humans intuitively understand what a circle is, but a redstone computer doesn't, and we need a more precise definition based on numbers and logic. We can define it like this. Every point on the circle must be exactly the same distance from the center, and this distance is the radius. For simplicity, the circle will always be centered at 0, 0, and to get the distance of any point to 0, 0, we can use a right triangle and the Pythagorean theorem, directly using the x and y coordinates. This gives us the distance squared, and we could take its square root to find d, but that's very difficult to do in redstone. Instead, we'll just turn d equals to r into d squared equals to r squared, and we'll also move r squared to the left. Now, we have the distance squared minus r squared equals to 0, or if we substitute using x and y, x squared plus y squared minus r squared equals to 0. So, since we know the basic logic, you might think that drawing this circle will be easy. Just make a grid for a screen and check which coordinates satisfy the equation. By the way, each pixel on the screen is 2x2 redstone lamps, and I'll visualize the coordinates as being the center of the pixel. But if we try that with a radius of, let's say, 10, it would look like this. Most of the circle isn't even drawn, because almost all points of a circle aren't exact integers, while our grid is made up of only integer coordinates. Therefore, instead of only checking for pixels exactly on the circle, we need to include other pixels that are close enough in order to fill in the gaps. But how do we do that? The equation we used was x squared plus y squared minus r squared equals 0, but let's just analyze the value of the left side. As I said before, this is the same as the distance to the origin squared minus r squared, and you can think about it as the approximate difference or discrepancy between the real distance and the distance we want. And let's call that the error. Of course, it's not exactly what the value represents, but it's more intuitive to think about it this way. So, if the error is 0, that means we are exactly on the circle. But if the real distance is slightly bigger, then the error will be positive and the point is outside of the circle. Conversely, a negative error means that the point is inside. I should also mention that the magnitude, which is basically the value if you ignore if it's positive or negative, it will get larger as you move away from the circle, and it will get smaller if you're closer to the circle. We'll use this error parameter and what its sign tells us a bit later, but let's first focus on the other problem with this current method. The method we discussed included scanning the whole grid, checking every single pixel, but this would be way too slow. For a 31 by 31 pixel screen, this would be 961 checks, and each of these checks include 2 squaring operations, an addition, and a subtraction. According to my rough calculations, this would mean more than 6,700 additions just for one circle, and that would take multiple minutes to do, which is unacceptable. The root of the problem is the scanning method wastes a lot of time doing unnecessary checks. It will check every pixel no matter how obviously wrong some of them are, so we need a smarter method. If scanning the entire grid is too slow, then what's the plan? You can pause to think about it. The solution is, a circle's path doesn't have any gaps, and so will our final drawing. Therefore, we can simply start on the circle and follow its path, and when moving along it, we only need to check pixels that are surrounding us, because we want the drawing to be continuous anyway. The machine knows where the circle is by knowing where it isn't. This also brings us to how to use the error from before. Simply compare the errors of the different pixels that we could go to and choose the best one, i.e. the one with the lowest error. But which pixels do we need to check? We will start on the right side at the coordinate r, 0, because we know that that's precisely r units away from the origin. Now, we can start moving pixel by pixel along the circle, and how we're going to do that is we're going to have a few pixel candidates. For example, I've chosen this one, and this one, and whichever one is closest to the actual circle, we're going to move to that pixel. But obviously, since we want our machine to be as simple as possible, we want to minimize how many pixels we are checking in total. In this case, it is 3. But can we get away with less? Or do we need more? So, if we're going counterclockwise, since the path generally goes upwards and slightly to the left, we can follow it with a combination of moving up by a pixel and moving upwards and to the left. If you think about it, only being able to go in these two directions means we are stuck between two extremes. Going up every time results in a vertical line, and going diagonally to the left every time, which results in a line tilted 45 degrees. And any angle of line between these two angles is possible to draw. On the circle, the limits are therefore here and here, because the tangent line, basically the direction of the path, is vertical here, and here it is at a 45-degree angle. So, just by checking 2 possible pixels in each step, we should be able to follow the circle and complete 1/8 of it, called an octant. In Redstone, I implemented these 2 move options with locked repeaters to store the current x and y, and the y value is fed into an adder to add it by 1, thereby making us go upwards, and the x value is fed into a subtractor to subtract it by 1, which we do if we also want to go to the left by a pixel. This brown line down here controls which option ends up being executed. But after this, the circle starts going predominantly to the left and slightly upwards, so these 2 pixel options no longer allow us to continue. Does that mean that we need to switch to checking the up left and left pixels, and we have to redesign everything? Well, that would introduce a lot more complexity to the checking logic, and actually, there's a much better solution. Why don't we just mirror the octant that we already have to produce all of the other ones? This is actually surprisingly easy. First, let's mirror over the y-axis, which is done by making each x-coordinate negative. Then we can mirror over the x-axis by making each y-coordinate negative. Then finally, over the line y equals x, which is done by switching the x with the y. This elegant solution means that we don't need the complexity of changing directions, and we reduce the total calculations and time required. In Redstone, I built this reflection module, and this series of reflections is done with what's called multiplexers, which let you select between 2 inputs. There are 3 multiplexers for the 3 reflections, one to select between x and negative x, one to select between y and negative y, and the last one receives the new x and the new y and can choose to swap their positions. This is run on a clock with a binary counter, which is just a way I use to cycle through all of the possible reflections for all 8 octants. So, just a quick recap before we go on. Our machine will draw a circle by starting at r, 0 and moving counterclockwise, each step either going up or up and to the left, depending on which one has less error. Each step, the reflectors will use that same coordinate and plot 8 different pixels to complete the 8 octants. And when the actual x and y reaches this line, y equals x, it will stop. But we haven't gone over how to actually compare the two errors. Now, calculating this manually isn't optimal, so we have another trick. Let's take the midpoint of these two coordinates right here, which can be expressed as the current x minus 0.5 and the current y plus 1. If this point is inside the circle, which is the case when its error is negative, then we should choose to go up only, because going up and to the left would just bring us further away. But if the midpoint is outside the circle, i.e. the error is positive, that means going up and left brings us closer to the path. So, to calculate the error, it is the midpoint's x squared and the midpoint's y squared minus r squared, and we want to check if it's positive. Change the midpoint's x and y into the current x and y, and this is it. We'll go over the redstone for this soon. By the way, this midpoint step is the namesake of the algorithm, which is called the Midpoint Circle Algorithm. Remember the 6700 additions we needed to do if we scanned the whole grid? Well, with the Midpoint Circle Algorithm, even the biggest circle in this machine would only need around 81 additions, but we can still bring that down even more. There is still one more hurdle to overcome to make this machine truly great. Notice that in the error calculation, there are 2 squaring operations that are required every single time. Squaring, which is multiplication, which in turn is done with many additions, is quite slow, and in fact it becomes more and more slow the bigger the numbers are. So, how do we avoid squares when every error calculation we need to do requires them? Well, we don't always have to calculate the error from scratch every time, and reusing data from the previous calculations actually saves time. Here's how we do it. The machine always starts at r, 0, so we can immediately calculate the error of the midpoint that we have to check right now. Let's simplify the expression with the x and y coordinates that we know, r and 0. Most of the terms cancel out, leaving us with 1.25 minus r. And the 0.25 doesn't actually matter, and rounding it off also means that our redstone only deals with integers, so we can just chop it off. This will always be the starting error of the midpoint. Next, if we choose to go up by 1 pixel, the error of the midpoint obviously changes, but instead of calculating the new error from scratch, we simply update the old error. This will be the new error, expressed in terms of the current x and y, and if we subtract it by the old error, again, most of the terms end up cancelling out, leaving us with 3 plus 2y. So, if we go up, by simply adding 3 plus 2y to the old error, we automatically get the new value. The other case is if we choose to go diagonally to the left. Doing the same process, we just have to add 5 minus 2x plus 2y instead. So, in Redstone, the error is stored in locked repeaters and it goes in a loop, going through adders to add it with 3 plus 2y or 5 minus 2x plus 2y, and a multiplexer chooses which output we want. This of course depends on our decision, which remember, depends on the sign of the old error. With this extra optimization, the biggest circle now only requires about 23 additions. And so, that's the last piece of the redstone build, and we can finally draw some circles. Finally, here is a circle with radius 9 being drawn in real time. By the way, if you want to do some further reading, the sources I used are linked in the description. And if you check the Wikipedia article, you might notice that the explanation there is a bit different. And I explain why it will always give the same result in the pinned comment. Overall, I'm really happy that all of the optimizations made it possible for it to run this fast. And you can try it yourself with the world download in the description. I hope this video helped you learn more about math, computer science, and redstone, and thanks for watching.